Good morning, Carol. Good morning, Matthias and Kai. Good morning, Corsine. And Felix, good morning. Stella, good morning. Waiting for a few others to show up here. Good morning, Sina. And Sophie, good morning. Well, while we're waiting, how's everybody doing with their online stuff? Hello, Isabella, good morning. Anybody experiencing problems with how teachers are doing things or how things are going? Or are things going relatively smoothly for you guys? Pretty good? Okay, that's good. If there are problems with how teachers do things, you can also let me know. I can send that on to the administration and see if teachers can do things better. Okay? I like to improve, and I want it to all improve for all of us. Good. I got Timothy P. I've got Liam. Good morning. That's good. What do we got? I'll give him another minute, and then we're just going to start up. There's Jack and Corey. Good morning. Ines is here. And Lauren is here. Okay, so I'm going to go ahead and start. So, what we need to do is finish up the different intermolecular forces. Again, that's between one molecule and another. So, again, we're not talking about a bond, right? That'd be like a bond. We're talking about an attraction between one molecule and the other. Okay? I'm going to send you out a data sheet so we won't meet the rest of the week. And the data sheet has to do with some amounts of energy to break apart bonds and to break apart intermolecular attractions. And you can see some actual numbers in joules or kilojoules on how much energy it takes to break up like a mole's worth of attractions or bonds. Okay, you'll see why I'm going to ask you that. I'll ask you some questions about it too. That'll be your assignment this week. But for now, we need to review something that 9F had, at least most of them, but 9E did not, and it's hydrogen bonding. Okay, when last we met, both groups, oh, Devante's here, good. When last we met, both groups had, I believe, dipole-dipole forces. And let's just review that, okay? So here's how that goes. We had, for example, F and Cl. And we said the story is on the periodic table that the closer on the periodic table to F, the more atoms like to pull the electrons towards them. We call it electronegativity. Okay? So F is more electronegative. What that means is the shared electrons in the covalent bond, they're getting pulled more towards the F side. So F side is more negative and the Cl side is more positive. We call that a dipole. Makes sense, right? Two poles, one positive, one negative. So dipole. So we say FCl has a dipole. Okay, but what that means is, hello, Charlotte. What that means is if I got another one down here, maybe it's going the opposite way. Doesn't really matter, right? I could just turn them around. Then guess what? They're very attracted to each other because they have a permanent charge on each side. That's the difference between the London dispersion forces and the dipole-dipole forces. Okay? So these forces and that's what we call it, dipole forces. And these are from permanent molecular dipoles. And just as a contrast, okay, London dispersion forces were from temporary dipoles. Remember, they form and then disappear, form, disappear based on their clouds of electrons just moving one way or the other. And okay, so those two types of forces are different. Now, sometimes one is stronger, sometimes the other. It just depends on the situation. So I can't tell you, oh, that's always stronger. It's not. Let me check a couple more people in. I got Aslan and Charlotte. Okay, anybody else out there? If you haven't said hello, do so I can check in. Okay. So last time 9F at least got to the third type of, or fourth, whatever number we're on. We've had London dispersion forces, now dipole-dipole. I guess it's the third type, but it's a special type of dipole-dipole force. And it's called, let's see if 9F remembers. So a special strong dipole force is called All right, 9F, you got it out there? Hello, Tim H. Good. Check in. Tim H is here. Yeah, Kiara's got it. So it is indeed called hydrogen bonding. The most important example, which we drew yesterday, we're going to draw again briefly now, is water. And water is bent. So here's some waters. And here's another water. And O is very much up towards fluorine. So O is very electronegative. So what we get is O is negative. That side of the molecule, that part of the dipole is negative. The other part is positive. Negative, positive. So you guessed her, okay? We're getting a strong attraction from one molecule to the other. And that's called hydrogen bonding. Okay? Now, once again, hydrogen bonding, it only occurs between, hydrogen and what? And who? It occurs only when hydrogen is attached to or him. The three magic elements to make hydrogen bonding happen. So 9F, folks, type it in. Okay, so from last time, hydrogen's got to be attached to who to make hydrogen bonding happen? One person's got it. Let's see if some others are going to type it in there. If you're awake this morning, Charlotte has it, Tim P as well. Good. So fluorine, oxygen, and N. And the cheesy way to remember is, do you remember? Yeah, exactly. So hydrogen just wants to have fun, right? Fun, F-O-N. Okay. Hydrogen bonding happens a lot in the human body, including like DNA. So it's a big deal. So for 10th grade, this is a big deal. I want to do a couple more examples now with everybody because I think we're all caught up at the same spot. And let's just look at a few, all right? So I'm going to erase this and look at my sheet and remind me what I was going to do. Okay. Goody. Here's another one, N. And N is attached to three H's, but they're like this. It's not very symmetrical. So all the H's are on one side of N. So that means, you guessed it, the N is more negative and the H side is more positive. So this sucker has a dipole, okay? And if I draw another one floating around next to it, then it's going to be N, H, H, H. And you guessed it, between the negative end here and the positive end, then I get some hydrogen bonding between the N and the H's in the next one. Remember, the name is stupid. It's called hydrogen bonding, but it's not a bond at all. It's an attraction. Okay? So it's an attraction, not a bond. I'm sorry, I don't like the name. The German name is Wasserstoffbrücke, which I like much better. Attraction. not a bond. Sorry about the name. I can't help it. Okay, so what good is this? Okay, it helps predict some stuff. Okay, generally, two things. Things that hydrogen bond, so I'll say molecules with hydrogen bonding, and I'm going to abbreviate that now, hydrogen bond. Two things. They, oh boy, I just had my little tiny brain. Okay, so, yeah. Have a high or higher boiling point than expected. And two, are soluble in water. Remember this from last time, folks that were there? It's like dissolves like. So if things have similar attractions, they dissolve in each other. And we're going to draw that right now in just a moment. Let me check a couple more people in. Isaiah and Michael are here. Okie dokie. Okay, so what does it mean if something's soluble? What does this look like? And that's what I want to look at with you now. Okay, soluble means one dissolves in the other. We said last time that oil and water don't mix. Why? Because water has hydrogen bonding. Oil does not. Oil doesn't have anything except for London dispersion forces, and the hydrogen bonding between the waters is much stronger, so they don't mix. The water stays with water. The waters like other waters better than they like oil. So if you shake up a container of oil and water, it will separate, and the waters all like each other and they get together, okay? Because of hydrogen bonding. So it's a big deal. It's a big deal. If I have an oil spill, the oil is going to stay out on the ocean. And it makes a solution. That's right. Alessandra is here. All right. Okay. So here's an example. Will ethanol dissolve in water? We're going to draw a little picture and think about that. And Malta's here as well. Okay, ethanol, if it's got an OL ending, can you guys remember? Yes, he did hear you. So you're all set, Michael. So ethanol, if it's got an OL at the ending, what's it got in it? Who remembers? We had this in a model building lab. We talked about it, but we also had it in a model building lab. And it was in the, it's okay, Nessa's got it. Good, it's an alcohol. So with two C's, right? Ethan, so two C's, so we go boom, boom. And alcohol means it's got one of these OH on it. Oh, but wait a minute. Hydrogen just wants to have fun. Look at it. I got a hydrogen and it's attached to an O. So it's looking like I might get good. Several of you knew that. I'm pleased. So will hydrogen dissolve in water? Well, let's see. What part of the water, if I draw a water molecule here, what part will be facing the O to hydrogen bond? Let's do that again. I'm going to draw water here. What part should I have face the O here to hydrogen bond with it? What part of the water should face the O when I draw it here? Think of like little magnets. Good. Corey's got it, and Isabella's got it, and so on. Good. Let's draw it together. So they say the hydrogen. So here we go. And sure enough, those suckers are positive. I'll kind of draw it on here. This side's positive, this side's negative. And over here, this side's negative, this side's positive. And notice not the whole molecule has a dipole, just this little end does of the ethanol. But that's enough. That's enough to matter. So I get some hydrogen bonding between probably, you know what I mean, between both H's and the O here in the ethanol. So indeed, the answer is, you bet, I get hydrogen bonding allows the waters to mix freely with the ethanols to make a solution, as Chiara called it. So allows waters to mix freely with alcohols. Well, ethanol. Or ethanols. Again, they both have hydrogen bonding, so like dissolves like. If they both got it, then that little phrase works really well to help us remember that rule. Yeah, so it's dissolving, Chiara, in water. That's right. Now, if I put ethanol in oil, it ain't going to do nothing. It's not going to dissolve because ethanol can do hydrogen bonding. Oil cannot. So it would not be like dissolving like. A dipole and a non-dipole won't dissolve in each other. And that's why the oil floats. Yeah, but if they're the same, yeah, they dissolve in water if they both have hydrogen bonding. Righto. Ute. Let me see how we're doing. We're doing okay. Let me let you catch up, and I'll blow my nose. Okay, hope you got that. Which would have a higher boiling point, BP? I'll write that in parentheses in case you don't know it. So the temperature at which it boils. HF or HCl. Okay, so they both got H's. And they're both going to have dipoles if you think about it. F is more electronegative, so minus plus. H is, well, sorry, Cl is also more electronegative, so minus plus. They both got dipoles, but what? Good, I got lots of correct guesses. HF is correct because F is more, thank you, Chiara, electronegative. And so it's got an even more hard of a pull than Cl does. So what that means is this, I'll say HFs attract with hydrogen bonding. Okay, these guys, the HCl's, attract with, in this case, less strong dipole-dipole forces. Let's see if I wrote that right. The HFs, yeah, attract with hydrogen bonding. These, so literally to pull apart a bunch of HFs, I've got to break a lot of attractions. Check this out. So I got to break that. I got to break this. You know what I mean? I got to break this. So lots of attractions. To boil something, to change it from a liquid to a gas, I've got to break attractions to do it. Must break the hydrogen bonding to form a gas. And I'm going to say really exactly, hydrogen bonding attractions to form gas. And with the other one, right, with the HCl, I've got to break a little bit less strong dipole-dipole forces. So with the HCl's, yeah, I got the same story, but it's a little less strong, okay? So I got something here, but I don't know. Anyway, you get the point, right? Okay, so I'll draw a line. So less strong. These are less strong. Good. Avram is here. Thank you. Questions before we do the rest of this? Avram, you need to watch the rest of the video and send me your notes because you're late. So I'll give you a half points here till I get the rest of that. Because you missed an awful lot, as it turns out, an awful lot. Okay, we're doing all right. I want to draw at least one other picture with you. But that's a really important example, okay? So hydrogen bonding or dipole-dipole, it matters in terms of boiling point. Some things then boil at it. So what that means is, I better tell you this. If I had HCl in a bottle that was pure HCl, I know I give it to usually as a solution, right? 1 molar solution or something. If I had pure HCl, it's a gas at room temperature. Isn't that weird? Usually I'd have it dissolved in water for you, so I make a solution. Pure, that's a gas, but HF, pure HF is a liquid at room temperature. So it does have a higher boiling point because the attractions are stronger. Stronger attractions, harder to pull them apart and make it into a gas. Okay? All right. Let me know if you got questions because this is pretty intense stuff. Okay? And these little pictures I draw, that's really what colleges and universities want you to be able to draw and explain. Little models with pictures like this. So if you can do that, bully for you. Okay. Okay, I got a related question about all this. And it's kind of something we did on the first day of class back in August. So the question is, why does NaCl or any ionic solid no, I'm going to say many, not all, many ionic solids dissolve in water. So think about the two things we've got. We've got NaCl and we got water. Water, as they say in New England. So we learned NaCl starts out like this, right? It's a big cube, and it's made of lots and lots of Na pluses, and in between them, big Cl minuses. And so on, right? You remember drawing that, right? A salt crystal, lots and lots and lots and lots of Na pluses and Cl minuses in a big crystal. Okay, blah, 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 blah. Okay, I hope you remember that. We'll draw one more just for grins, but you get the idea, okay? And remember, Cl minus is bigger because it's got an extra electron that makes it bigger. That's why I don't draw them the same size. Cl minus really is bigger. Okay, I'm going to put this in a bunch of water, so let's see what happens, okay? So I'm going to draw a giant beaker. Ready? Here's my beaker of water. Woo! Okay, and there's my top of my water. So I throw this chunk in there. Wham! Well, here's a water, right? And we already said water has a really important dipole. This side's positive, the other side is negative. Good. All right, so now see if you're ready to type me a little answer, everybody. Why does this break up in water? What happens there? What happens to the Na pluses and Cl minuses when they get in here? Yeah, I'm going to draw another water over here too. I'll draw a bunch more. Let's draw one here too. Okay. All right, Alessia, you can watch the rest of the video when I send it to you. Okay, don't sweat it. Okay, so back to our question. Why does this stuff dissolve in water? What's going to happen, everybody? Liam's on a good track. He says it pulls the NaCl apart. He's right. So the NaC gets pulled apart. And what happens to the parts of this? Explain what happens to the different parts. Okay, they bond. They attract. Careful, Tim. Tim H. They don't bond, they attract. But what exactly are they? Can we be specific? Okay, the Na, Timothy P says the Na is more attracted to the O, and I assume that means the O in water, and the H is attracted to Cl. Yes, close, 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 Tim. Aslan says the Cl and Na separate because they have stronger attractions to the H, and yeah, right. Okay, now you're on a good track too, Aslan. But there ain't no Cl. There's only Cl minus. There ain't no Na, gang. There's only Na plus. So be careful. Okay, so same with Inessa. So yeah, it's separated. That's right. Okay, and the Na and Cl, but with their charges, attract. Okay, so here we go. Take them one at a time. Na plus. Tell me where to draw it, gang. Na plus. I'm going to get the blue marker. Where am I going to draw my Na plus? By which side of the water? Good. Okay, Timothy Peduso's there. it's going to go to the O side. So I'm going to put an Na plus down here. That sucker's going to snuggle up to the O because the O's negative. Here's another one. Oh, I get it. All right. I know it's early in the morning. It's the best I can get for cheap jokes. Yeah, so in water, I got Na pluses that snuggle up to the O on each side. Okay, so what about the Cl minus? Where does that sucker go? The Cl minus goes to the positive side, right? Which everybody's the what side of the water? Inessa says the H side. Yes, she is right. So here we go. So draw yourself some Cl minuses by this, right? So these big guys are going here, and snuggling up to the other side, aren't they? Look at this. This one's between a couple of them. That's fine. So that's what dissolving. Now, what we call this is, you ready? This is called dipole ion attraction. Or attractions. Ta-da! Water's got a dipole. Ions obviously have charges, otherwise they wouldn't be ions, duh. And so they're attracted to each other, and that's how we draw it out. If you can understand that, you're on your way to getting a good start in 10th grade chemistry next year. Do you guys have any questions about this stuff? That went pretty well, actually. Let's see if there's one more thing I want to ask you about. That's pretty much it. Ba-dum. You got it. Okay, so here's what we're going to do. I got to tell you what the scoop is, okay? What do we got here? We got Wednesday. I'm not going to meet any more this week with 9E or 9F. You are done with my meetings for the week. But I will assign something to do, and it's going to be a sheet of data. And importantly, the energy will be the energy to pull apart the attractions, or in the upper part, the energy to pull apart the bonds, okay? And I'm going to ask you some questions about that sheet. I don't think it'll be real hard, but it's pretty cool data, so I hope you like it. I pulled it off the internet yesterday. Looks like a really good thing to have you think about, okay? That's it. We'll do something new next week, but I just want you to digest this the rest of the week. Email me if you got a question about the worksheet, but I'll probably have it due. I don't think I want to do Friday because this is Wednesday already. I think I'm going to have it due Tuesday because that way Monday in our live stream, you guys can ask me if you want to ask me something. And we're going to submit it in Google Classroom, right? So I'm going to have you do your answers on a separate Google document and then upload it into Google Classroom. Yeah, let's do that by Tuesday, okay? So I'll put the due date on it and send it out to you sometime today, okay? The sheet, I will send you the assignment with a copy of that sheet real soon, like once we're done here. Okay? Any other questions from you? Now we're going to end early, and I'm going to wish you a good dipole day out there. Okay? Stay healthy, and thanks for doing some chem with me. We'll see you for our live stream probably on Monday. That will be the next time. Bye-bye.